In this video, we'll formalize some of the intuitive understanding that you probably already have for probability. So if I give you a question like, I have a six-sided die, and I ask you, what's the probability that it comes up 1, you can probably answer that. So you could say, well, the probability that it comes up 1, there's 6 faces, they're all equally likely, so that's 1/6. Easy enough, that's intuitive. But to do mathematics with it, we need to give a formal definition to what this function probability is and how it works. So let's go back to our example of the dice. First, we need what's called omega, or our sample space. In the dice case, that's 1 through 6, because there are 6 possible sides of the dice, and so they represent all of our possible outcomes. This omega is called the sample space. The elements of it are called outcomes, and subsets of it, like if I said let A be 1 or 2, this is called an event. So this is the sample space, this is subsets of the sample space called events. Now the probability function takes elements of the sample space to real numbers. All this notation means is probability acts on sets that are subsets of this sample space. So for example, P of this set 1, and it takes it to real numbers. So they're just numbers that you think of, everyday numbers, you know, a half, a quarter, square root of 2 over 2, anything like that, that's a real number. Just no imaginary numbers. So probability is a function that takes the sample space to real numbers, and what other properties does it have to have? So there are properties of probability. Properties. What are they? Well, first of all, it has to be greater than 0. So, or greater than or equal to 0. You can't have a probability less than 0 because 0 means it doesn't happen and there's nothing less than not happening. The second is that the probability of the whole sample space, meaning all of the outcomes and events of interest, at least one of them has to happen. So if I say take the whole space, the probability of that is 1. So if this is my sample space, I'm not going to get a 7 because the probability of the whole thing, any number 1 through 6, is 1. And finally, this is a little more technical, but it's still very important. So if A and B are disjoint, and what does that mean? Let's refresh our memory there. Disjoint, meaning A intersection B is the empty set, the special set with no elements, then this implies that the probability of A union B is equal to the probability of A plus the probability of B. Graphically, that's like saying if our omega, so let's draw omega, if you think visually, if this is omega, and this is A over here, and this is B over here, and they don't overlap, then the area of this and this is just the sum of the area. So that's just saying probability, the function behaves kind of like our intuition for areas says it should. One more thing about this is, what if I have A, B, and then I throw in a C, and that's also disjoint? What can I say about the probability of A union B union C? So pause for a second, think about it, and try to figure it out. Then unpause it. Well, I want to treat this like its own event. So A union B union C. Remember, union is associative, which means that this is the same as this, where I group these two together first, which is the same as this. So if I write that as the probability of A plus the probability of B union C, then I just apply the same thing down here that I just applied. And naturally, I think you can generalize this if you think about it a little. So what happens if we have probability of A1 union A2, all disjoint, union dot dot dot, all the way up to union AN. So some arbitrary number of sets, they're all disjoint. Well, then that should just be the sum by induction of the AI's as I goes from 1 to n. And this is even true for infinitely many sets, but we're not dealing with that right now. We're just talking about finite sample spaces. So these are the basic laws of probability that you have to know so we can play the game in this course.